Assalamualaikum warahmatullahi wabarakatuh. So in this video I'm going to show how to do pin element simulation for blanking operations, or blanking or punching operations. So in this case, look into this one case where pin elements analysis of blanking operation, a series of punching tests were conducted with a 1 mm sheet in here. Okay, 1 mm sheet in here. So you can see this is the tool number 2, this is the tool. Okay, this is the tool. Okay, and the sheet is this. This is the sheet, and this is the die, and this number 4 here is the stripper plate. Okay, this is blank hold, or we can say stripper plates or blank holder. Okay, so this is number 4, this is the punch, and this is the sheet here. Okay, this is the cross sectional area of the die for the punching. Okay, but this is the case where 2 mm punch being used. So this is 2 mm punch. Okay, and with a 0.1 radial clearance. Okay, this is the C. C is we can say 10%. In this case it is 10% from the punch diameter. Oh, sorry, yeah. Okay, so first what we need to do, we need to draw the geometry. So how is it looks like? So in this case, since this is 1 mm, so you can see it here from there to there. Since this is radius, so meaning that if we want to do the full set for the punching, this 2 mm. So this is, since we're going to do symmetrical half, so we want to limit this our analysis just to focus on, since we want to focus on this part where we want to see the effect of the clearance. Okay, the clearance here, about 10%. so from the total punch, and the thickness here is 1 mm. So that's why if you look carefully here, there is the radius for the punch, it's 1 mm, and the thickness, sorry, we can turn back up. So this is 1 mm. So okay, what you need to do is that you have to draw this on paper first, so that you can do this, because you can locate each node here, each edges here. Okay, so this is the case where we start from 0, so we assume that here to there is 0. Okay, start from this point, so meaning that point here is 0, 0, and on Z direction is 0, so meaning that X, Y, and Z. So we just focus on XY first, since we're going to do two axis symmetrical geometry. So because what we intend to do is this, where we assume that the whole thing here is round. Okay, all of this is round. Okay, actually it is round. So then they are all round. So meaning that okay, meaning that we only draw this part here only. 2D geometry. That's why we need to locate each coordinate. Okay, from there, say why you start from 0 0 here, so go to up here. We decide it to be the thickness of the thickness of the die is 3. So that's why you start from 0 3 for the sheet. Okay, from here 0 3, and since this is 1 mm, so 0 4. Okay, 1 mm thickness, and then we go all the way to the right. Towards the end, we decide this the diameter of the radius of the sheet, or the blank. We call it this blank as well, or blank, or workpiece. It can be called workpiece as well. So, to be 4 mm. So including the the clearance here. Okay, see here 0.1 mm. Okay, so this gives us 0.4, and then 4.1 and 4, and here is 4.13, and then we can draw this die here 1.10, but point here is at here 1.13, and here 4.10. Okay, since we have 4 nodes, and it's okay. And for the sheet, okay, set. Okay, now this is done. This is done. We have the location, and here we decide this blank holder to be 1 mm thick. So 1.14, 1.15, 4.15, 4.14. So we have this one settled. Okay, then here we know that the distance between here 0 and 4.1, if 0 and 4.1. okay, right? Sorry, 0 and 1. Yeah, 0 and 1. Okay, but why do we start from 4.1? What the reason is, we want to introduce a very small gap before the punch. This punch make contacts with the sheet. So in every LS-DYNA simulation, or in every finite element simulation, it's always like this. You have to introduce some very small gap, okay, before this object make contact with this another object. Okay, so in this case, blanking analysis, we decide this one to be have 0.1 gap, 0.1 mm gap. Okay, then it's okay. Okay, we can also use 0.05, 0.2 is okay, but then in this case I just introduce exactly the same like this clearance 0.1. okay, that's why I put here 4.1. go, so meaning that here 0.4, So then plus 0.1 we get 4.1, and here at this I decide to be 0 and 6.6, where I decide this to be 2.5. Okay, you can make it longer, 3 mm, 4 mm, doesn't matter, but then that increase the number of mesh, since we are going to just to assume that this punch as a rigid body, so it's useless to make it long. Okay, just enough to have this punch but moving just down towards the bottom and cutting this sheet. Okay, so since we are finished with the coordinate, so we go for this. So here you can see here, this is the mesh here, right? The mesh, okay, and the strip, okay, stripper blade or blank holder. Here the sheet, or we can call it blank, okay, and the die. So here, as you can see here, I already make some very fine mesh in this area, because I want to, since this area is the cutting area, and the punch making contact with the cutting area here is around this area. That's why I make it small mesh around here only. Okay, so the rest you can leave it as big as possible. That's not it's not going to affect the accuracy. Okay, but please bear in mind, the smaller the mesh, the higher is the computation time. So you need to have some suitable number of it. So that's why something you need to do is that, since this is related to the accuracy of FE results, okay, what people normally do is that they will perform convergent tests. So they will, how they do this convergent test? What they do is that they play around with the mesh sizes. So in this case, they will focus in this area here. Okay, they will decide maybe the size there, maybe first for first trial, this trial, they perform this using maybe with big size. Okay, for example, with 0.1 mm size, and then they do the second try. Okay, maybe somewhat around intermediate. Okay, 0.05 mm. Okay, around here, and then they reduce a little bit more, maybe 0.005 mm, and then they reduce even further smaller, 0.01 mm, and then they plot the results. So let's say they perform the test, so they look into the force as a function of displacement, for example, or maybe time. So they will see it, say they perform the test, so they will see. So maybe this one from number 1. So since they have the experiment, let's say they have the experimental value. Let's say they have experimental value this way. Okay, this is experimental, for example. So then they go for the second one. So maybe the second trial, they have something here. So maybe the third trial, they have something around here, and then fourth, they have somewhat similar fourth. So in this case, if you look closely at this here, okay, which one is close? Which line is closer to the experimental? The green point here. of course number 3 and 4. So meaning that number 3 or 4 is a suitable candidate. Okay, so it's a good choice lah, good choice for mesh. Okay, so that we can ensure that we can get very high accuracy. Okay, high accuracy. Oops. Oh, they lost. So meaning that if you we know that this is the force there, number 1, number 2, and then number 3 and number 4 somewhat similar. This is the experimental value. So in this case we can see that the good candidate is number 3 and mesh number 3 with 0.005 mm, and number 4 0.1 mm is a good choice. But do you need to choose this? You don't need, right? Since number 3 is also fit, give the best fit to the experimental, right? To the experimental force. Okay, so meaning that if so meaning that here is just enough to select this one only. Okay, we go for this. That's it. That's what they call where you perform the convergence test. This ensure the high accuracy of FE results. Okay, so then let's try with let's go and try this. We draw this. Okay, so what you need to do is that you launch the LS-DYNA program manager. Okay, you open, you click on the LS pre-post, and then you click on start. Okay, and then you go to the right, you see this element and mesh, you go up and you see shape measure, and you click on it. Okay, since we are focusing on making 2D analysis, and we want to do this is what we call shell elements. Okay, so with this coordinate here, so we can create the first one, we create punch first. Okay, so you click here, you go for 4N shell, meaning that 4N shell meaning that you have 1, 2, 3, 4 node. Okay, then you create the shell element. Okay, you can also click box solid, box shell, it's up to you, but in our case we choose 4N shell. Okay, so here we need to identify, enter, so you can see here, right? Enter XYZ. Okay, 4.1. Okay, since we have here 0.41, 4.1, and then see here we assume 0, and then okay, and then here the next point here 4.1, right? 1, 4.1, 0, and then we click here 6.6. okay, 6.6 and 0, and the next one 6.6. okay, 6.6. okay, then this is number of mesh. Okay, so you can put you can name this. So let's say we name this punch. Okay, and target number, the part number ID is 1, so we click on here, create mesh entity, create. So you can press control and then rotate your scroll, okay, so that you can zoom out the object here. Okay, you can see here, right? This is number of mesh. If you do not satisfied, what can you do is that you can click on reject. Okay, then you can also click again. Let's say here you want it to be in X number of meshes in X direction to be 10, and number of meshes in the Y direction to be 15, for example. Then you click create. Okay, then you have something like this. Okay, then is see that okay, this is look fine, and still you do not satisfy, you can increase the number in Z direction to 20. Okay, then you have something like this. So then you, if you satisfy, then you click OK. Then you have part number 1. If you click here, this is what you get, punch. You click on the punch, this is your part ID number 1, punch. Okay, so you unclick this. Okay, then okay, zoom out a little bit. Okay, now we want to draw the next part. Okay, the next part is part ID number 2 is here. So then for part ID number 2, we're going to draw this sheet material. Okay, so we call this name sheet, and then we need to locate the coordinate 0, 3. We start with here 0, 3, 0, and then we'll go to the next 4.1, 3, 4.1, 3, 4.1, comma 3, and Z 0, 4.1, 4.1, 4, and Z 0, and last one 0, 4, 0, 4, 0. Okay, okay, so then you have the part. So then you click on create. See, you have this. Okay, since you say that you think that this is not satisfying, so you want to reject. So what you want it now, you want to increase the number of the mesh here. You want it to be let's say 80, for example. Then you click create. So then you said okay, this looks fine, then accept. Okay, then you have this part number 2, right? So we go for part number 3. So now it is blank holder. So now we name this blank holder. Okay, look here. So then we start with first point 1.14, 1.14, the next point 4.14, and then 4.15, then we go 1.15, comma 5, and click enter. So this is too much, right? So since this is just a die, so it is a rigid body, so we want it to be less. So let's say we say this is 30, this is here is 10, for example. Reject. So click create. So you think this is okay? So maybe you want to reduce a bit more, 25, and then you go for 8 here. Okay, then you said okay, this is okay. Okay, so then zoom in, zoom out. So you have part number 3. So we go for part number 4, which is the die down here. The die. Okay, we start with this here 1.10, and then 4.10, and the next point 4.13 1,3, and last one 1.1,3. Again, we try to look at the number of meshes, so it seems that it is too big. Seems not suitable, so you want to reject, for example. So then you say this is 10. Let's say you want it to be here maybe 30, for example. Create. Okay, you say okay, maybe this is fine. So then you create then accept. Okay, then finish. Then you have the part. So if you want to check your part, you can click here model and part, and then you go to keyword manager. Okay, you can do not click all, you click on model only. Okay, so here you have part number, punch, sheet, die, blank holder. So then also notes is available for each part, for each components, and shell also available for each component. So you don't need to check the element and nodes. It will be automatically generated for you by this LS-DYNA software. But what you need to check is the part here. Okay, punch, is this part ID number 1? Okay, that's correct. Sheet, part ID number 2, yeah, correct. So here, and die number 4, okay, so they are all same. Okay, that's okay.